All right, stop talking. Hello. Welcome to the internet. Not like the actual thing, a lesson about it. By the end of this lesson, I hope you will be able to describe what happens when you type google.com into a browser and hit enter. The setup for this lesson was Stacy asking about, well, this is a really common interview question. My tech buddy said that this is the one thing that everybody always asks in an interview. I'm kind of inclined to agree. I don't think it's that common, but it's a really good question, and unlike a lot of tech interviewing questions, I don't think it's a stupid one. I think you can find out an awful lot about someone's technical knowledge from how they answer this question. One of the reasons for that is that it's kind of a fractal of a question. You could probably give an answer to this right now that works on some level, but we can go down to like electrical connections and OS interrupts and writing to memory and all kinds of other shit along the way here. So we can go down arbitrarily deep on it. We can go down to what Kyle's mom knows about what happens when she types google.com and in Facebook and hits enter, all the way down to like physics and stuff, and lots of different mile markers along the way. So what I'm hoping is that by the end of this lesson, whatever you can do right now, you'll be able to get a little bit farther. So let's benchmark that. I want to take, let's give it maybe 3 minutes. If I were to ask you this question right now, why don't you give your best answer for it? So 3 minutes on the clock. Go for it. About another minute. Much detail as you can. All right. So we're going to do a turn and talk. We're going to do tears. Danny, you're with me. share your responses. Go. All right, what you got? Okay, so how does that relate to that? Like lots of pieces in there, but I type google.com, I hit enter. Which of those things are happening? Yes.
But it is a general request.
Which is why we would consider without like adding more listening.
Yes.
Oh, just that I was just talking about why I said that it will like default to get, and that's why I didn't bother saying anything about their controllers.
All right, so back with me. So lots and lots of layers on this. Let's start unpacking them a little bit. Fundamentally, we've got browser over here. Some Google server over here. We make a request to them. We get a response. Let's start filling in some more detail. You can give me some more detail about this. Carl.
The first thing you do, you type in google.com. It checks, have I been to google.com before?
Okay.
I have the IP address for this already. I'm done.
Cool. So that process of getting the IP address, what's that called?
DNS.
Yes,
So,
correct. It's DNS lookup.
thank you.
All right, so I type google.com. My computer doesn't know what the fuck google.com is. All my computer knows is IP addresses. So we have a variety of different phone books that map URLs to IP addresses. One of them is in your computer. So if you've been to google.com before, it'll go, all right, awesome. I know what the IP address for that is already, because I had to look it up last time. Next, so I might say this one's your computer. Anybody know where your local DNS doesn't know what the IP address is? Any guesses what the next one is? Next place it looks? In a way, but there's actually one even before that. I'm going to say that your ISP is probably this third one. What's in between your computer and your ISP? Exactly. If anybody on your network has been to google.com, your router is caching these IP addresses also. All right, your router doesn't know it. Or in either of these cases, it goes, I know it. They might have changed it though, and the note that I got the last time I looked it up is that I should honor this for 300 seconds, or 3,000 seconds, or 30,000 seconds. However long it told me that like this address is going to be reliable, I'm going to keep giving you that address. You can imagine a situation where the IP address changes and you have a cached one that isn't accurate anymore. Anybody ever tell you like, reset your DNS, unplug your router, that kind of shit. That's what they're trying to do. Blow out your DNS cache. That's my favorite sound as a teacher. All right, so your ISP doesn't have it. Any guesses where you go next?
Eventually getting up to like a root server, domain.
Correct.
Which would be .com in this case.
Yeah, so anybody know who owns .com? VeriSign. And lots of things in between. So your ISP throws it up to some internet backbone. They've got stuff cached. That internet backbone throws it up to somebody else, throws it up to somebody else. You look at who you registered it with. So like AWS's Route 53, Namecheap, any of those kinds of things. And ultimately, yeah, it's going to go to a root DNS server, which is probably run by VeriSign. Fun fact, if you are mischief-minded, you might realize that you could break the entire fucking internet if you just hacked that. Don't need to do all this. Don't need to destroy HTTPS protocols. You don't need to do any of these like actually difficult things. If you can just crack VeriSign's stuff. Somebody tried like 2 years ago. Got pretty far. Oops. So yeah, these are all just phone books. Do you have the IP address? 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 Do you have the IP? I do. Cool. I'm going to give it to you, and then 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 ultimately back to your computer. Questions about that?
Shouldn't that take a really long time?
You think so? No, it is shockingly fucking fast. But keep in mind that due to the nature of this, we're not going all the way to VeriSign every time. That would be like your buddy's website that nobody's ever been to before. And so it's not cached anywhere. But remember, even if your buddy went to your buddy's own website, I don't know, do they use the same ISP? Are they in the same geographic area? At some point, one of these things probably has that IP address. That shortens the route a little bit. You guys want to see what it looks like when you like actually assign this stuff? I think it's kind of interesting. So if I go over to the AWS console, and authn, cool. So this is the Develop Denver AWS. All of our URLs are registered through Route 53, which is one of Amazon's services for that. So developdenver.org. The actual telephone, this goes with this thing. It's called an A record. The A record for this says that when somebody types this in, it should go to one of these two IP addresses. If this one's down, try this one. Pretty fucking cool. Those IP addresses, by the way, are Firebase IP addresses. So they're owned by Google. Because that's Firebase is where the front end for the app is hosted. So that's where the request is actually going to end up going. We also have these other things. MX is mail exchange. So if you have a developdenver.org email address, you want to reroute that request over here. The NS is name servers. This is like the VeriSign, like this is the root thing. I have no idea what an SOA is. This text is just metadata. It's Google's site verification. It's how this routing to Firebase works. You have to have that so they know that I know the secret key. And then the CNAME is an alias. So that if you type developdenver.org, it goes to this IP address. If you type www.developdenver.org, it just reroutes to that. Because those are technically two different addresses. Yeah.
Start of authority, basically.
There you go. Start of authority. I still don't know what it means.
That's still.
Cool. That's IP addresses, and that's all it is. Questions?
Like for someone like Google, I mean, how many IP addresses might they have?
Someone like Google. Probably not as many as you might think. It's not like millions. They'll probably have, well, actually, that might be a little bit different with their cloud infrastructure. They probably have a bunch of IP addresses for that. But like for their own stuff, probably not that many. Because all you need to do is route it to something that Google controls, and then they have subnets. That's all those billions of possible IP addresses. You get to do that again once you've gotten to the correct location. So they could have a billion different like internal IP addresses that they route requests to. Was anybody around for the IPv4 v6 horror show? What was that, Carl?
I guess the short version is we've run out of IPv4 like base addresses.
Correct.
So they're still sort of trying. Like it's always like, oh, maybe next year, maybe next year. Get ready for it. They're trying to move over to IPv6, which has how many trillions more?
Yeah.
Just so we can start distributing addresses like we used to.
So, no, that's pretty good. So, these IP addresses are 0 through 255. Four sets of them. Two. Nope. 255. 0 through 255, 0 through 255, 0 through 255, 0 through 255. That's your unique address on the internet. As you might imagine, when they designed this scheme, they didn't know how big this was going to be. So we ran out. And we ran out a lot quicker than we might have otherwise, because when they created this scheme, which, as Carl pointed out, is called IPv4, we did things like say, well, IBM is a great big company that'll be around and like dominant forever. Let's give them like, I don't know, 1/10 of these IP addresses. So there was like particular ranges in here that were like pre-allocated to organizations. Some of them don't exist anymore. Some of them aren't as like dominant as they were at the time. And so some of them, like huge swaths of this, are just like for testing purposes only. All right, well that's a couple billion. So we ran out of these. We replaced it with a scheme called IPv6. It doesn't follow as consistent a format as that. Well, it does, but I don't remember it. IPv6. IPv6 addresses look like this. And so we can get way more addresses on that. In particular, 3.4 times 10 to the 38th power. Woof. So IPv4 was 4.3 billion addresses. This is 7.9 times 10 to the 20th power times as many addresses as that. We're getting into that like number of atoms in the universe kind of level with that. So we're probably fine for a little bit. Neat.
It'll last a little bit longer.
Yeah. So, cool. That's this part of the journey. Other questions about DNS lookup? Yeah, Carl.
Just kind of like you said that, people that passed it, I feel like that's still kind of going on, like they're still trying to make that migration.
Not really. It's not an urgent thing anymore. Enough people switched over, and IPv6 addresses are backwards compatible. They just leave the rest of it as zeros, and that'll just work with the same IP address. I don't know that anybody's panicking about IPv4 anymore.
As long as you subnet everything.
Correct. Cool. What else? Other questions about how this works? Here's what it looks like in your browser. Google.com. I take a look at the network request for this. Oops, that wasn't it. There we go. I requested www.google.com. Get request. The remote address, that's the thing that I looked up, is that. And to wit, if I copy 172.217.1.196 and I just put it into my browser, weird, takes me right there. What's this 443 on the end? Not Carl. Yeah, Alexis. Nope, great guess. You're in the ballpark. So we're making a GET request to this IP address at this, starts with a P? Port. So in addition to sending the request to that address, you can think of it like when you go to like mailboxes, etc. Gee, that was a really old reference. When you go to the UPS store, where they have like a bunch of mailboxes, and you go, okay, well that's the address. Which one of these mailboxes do you want to put it in? Those are ports. And so there's a couple standard port numbers that, without doing anything special, that you will send your message to. So if I'm sending this request over HTTP, it's going to go to port 80. If it's going over HTTPS, it's going to, guesses? 443. That's why, like, if you've ever used, I think Light Server might do this, they'll set the port to 8080. Because that's like a generally not used range for public internet. It's just 80 twice. Cool, so I am sending a GET to 172.217.1.196 on port 443. Found the address, putting it in that mailbox. Cool. What's this business? What's GET all about? What technology is that using? Ooh, we gotta get this one down. If you're like fuzzy on DNS, you'll live. This one, we gotta know this one really well. It's web developers. Correct. We're using HTTP to format this request. I go, cool, this is the address I need to send it to. What am I sending them? What I'm sending them is an HTTP request. All that is a bunch of characters in a particular format. That's all there is to it. So if I look up raw HTTP request, see if somebody will give me one we can look at. Perfect. It looks like this. This is not like an example of like the kinds of information that's being sent over. It's literally like these characters. It looks like this. Send over a bunch of characters that look like this, and when that goes into the right mailbox at the right address, that server knows how to decode this and like get instructions out of it. Three parts to an HTTP request. What are they? What was that? Not MVC. We're still just in HTTP land. MVC is over here. Three parts to this request. Carl.
You can say like the verb,
Mm-hmm.
get, post, whatever, an address or direction it's going to.
I'm going to keep that as part of the same thing. So verb, address. I'm also going to put version up here.
Okay. Just a little headers and
Except we don't want to use that word because this next part is
that's the actual, okay.
headers.
The last part would be the actual payload.
Yep. Body. HTTP request. Version HTTP version 1.1. Get this IP address. Include these headers. Headers are key value pairs. So like you've done things like content type application JSON. That's a header. And body is optional. But it's if I'm sending you data, here it is. I'm creating a new user. Here's the user information. That's where that goes.
When we go to params in Rails, that's what params is.
Yep. So in the actual request, get this version. These are all headers. And if there was something we're sending over, which you can't do with a GET request, but post, put, any of the other ones, we can add data in there also. It's the structure of an HTTP request. Questions about that? Cool. And then we get what? Yes. HTTP response. Just like the request, all it is some characters that are formatted in a particular way. Just like above, we have like some like fronts matter. In this case, what? What's the equivalent of like verb, address? Still have version. What else? $200 is an example of this. $201, $404, $500.
Response code or something.
Status code. Status code. Status message. 200, okay. 201, created. So we get all these things back. Any guesses what the other two things are?
Headers and body?
Headers and body. So headers are key value pairs about the thing that we're sending back. Body is the optional content of the response. So something like a GET request generally doesn't have a body. A GET response almost always does. And the cool thing about this, you may not have realized, that's where your HTML goes. Saw a little example of it up here. Good, perfect. Version, status code, status message, headers, body. It's just the characters. Whatever the characters of your document are, come back in that response. Cool. So that's the simple loop. I type google.com in to look up where that is. I send a request using the HTTP protocol to that address, this mailbox. It sends me a response with version, status code, status message, headers, body. My browser goes, I know these HTTP responses. I know what to do with this. I also speak HTML. So I'm going to pull that body out. Since you told me that this response type was content type text HTML, got it. I speak that. So I'm going to take all of this and use my little HTML interpreter to make that show up on the screen. Ta-da. Now, next step, and this is like kind of where we come in as web app developers. Think about every HTML document that you've ever seen. We make the request, we get it. Give me HTML. Here you go. And as it's working through that HTML, what things is it going to run into that need to turn into other HTTP requests? Style sheet. Cool. Also, I need this style sheet. Styles? Here you go. Same protocol. The body is going to be CSS. The content type is going to be text CSS. What else? JavaScript? Sure thing. Here you go. This is text JavaScript. That's cool. I speak JavaScript. My mother was native JavaScript, actually. Stupid. So we get JavaScript back. We're going through the document, and every time we hit one of these lines, makes another HTTP request, takes the response, adds it to this thing that we're building called the what was that? Nope. DOM. This is what the DOM is. So as we're taking that text to HTML, we're making these DOM elements. Then we get the style sheet. And we take those rules in the style sheet and we go, cool, which of these DOM elements does this style apply to? Cool, this one matches, and this, and this, and this. So I'm going to say that this color is red and the padding is this. I'm going to apply all this stuff to that node. And I also have this thing that takes my finished DOM tree and renders it. Makes it just show up visually on the screen. And it knows that when this thing says padding 24 pixels, there should be 24 pixels here and here and here and here. And one other piece of this is what you guys have been largely learning how to do this mod and will do for the rest of the program. Cool, got to the bottom of the page, everything's loaded up. I've got a DOM. Now somebody clicks on something. That triggers a fetch request. That's another HTTP request. So these things can just keep going. And with the response, we can modify the DOM. We can do all kinds of cool stuff. Key thing you have to understand about this, the HTML, the CSS, even the JavaScript, like write it out in text, comes back in the response, and is parsed into the DOM, or the runtime in the case of JavaScript, and thrown away. Your HTML's gone as soon as it gets like digested by the browser. Doesn't need it anymore. Turned it into the DOM already. And one of like the bigger mind fucks, this is not like the browser doesn't have this anymore. This isn't what I got sent back. When you're looking at this in the element inspector, it's actually re-HTMLified the DOM. I asked for HTML, I got it back, pooped out the DOM. That's what's on the page. Hey, what is the HTML element that this represents? Shit, he wants to see it. Let me re-HTMLify this real quick. Let me get that.
Question for all the requests and response that are going back and forth.
Mhm.
Is anything happening to like make that connection faster, like between your device and that server, or is that just like, is there like a specific network connection that's created?
No. So you're talking about a thing that is like very hot on the web right now. Oh yeah, shit, I forgot. Any images you need, any other assets, movies, third-party JavaScript files, all that kind of stuff. Does HTTP requests for all those too. So if we're making a bunch of different requests to the same domain, seems like there should be something that like speeds that up. Not in HTTP 1. HTTP, and also like kind of funny thing that also I think the original browser vendors might not have made this part of the spec if they'd known how big this is going to be. You can only do 6 at the same time. So if you have 20 HTTP requests for images and JavaScript files and all this kind of stuff, it'll take the first 6, wait for those to come back, and then the first one that comes back, it'll start the next one, and then the next one, and the next one, until you get all of them. HTTP 2 was supposed to fix this problem and speed up these requests by doing a thing called muxing. So instead of each of those being discrete requests, it's like one request, it keeps a little connection open, it sort of streams it back and forth. It's two-way communication. So once that thing is open, I can just send you a message down the pipe, and then you give it directly back to me without all of the overhead of these kind of independent requests. The problem is, and so like just time-wise, we're probably talking about 4 years ago, 5 years ago, HTTP 2. And it worked okay. The problem is that HTTP 2 had some problems with what to prioritize and didn't always make great choices. And so 2020 is the year of HTTP 3. Everyone's like, oh, hold on, that was actually a pretty bad idea. And so trying to fix it with HTTP 3. But a lot of it is designed around speeding up those connections. You guys might have figured out from your hackathon projects, maybe not, that we generally don't ship a bunch of different JavaScript files or a bunch of different CSS files. Before we deploy, we mash those into one JavaScript file. We mash all the styles into one style sheet and then send all that down, even when we didn't write it that way. That's because the most expensive thing in every web app, network request. So if we make fewer of those, our app gets faster. HTTP 2 sort of turned that on its head a little bit. I was like, it's not any more expensive to make a separate request, so just keep them all separate. And actually, we might even be able to prioritize it better. Well, they didn't, so. But that's kind of where that is. Good question. questions about this. These like, as we're parsing the HTML into the DOM, keep making all these other requests, gradually building this DOM. Questions about that?
Do those boxes represent browser and?
Yeah.
Okay.
Exact same thing. But instead of this kind of high level, well, we make a request and we get everything back. This is the first one, and it triggers off an arbitrary number of other ones as it's trying to get the pictures and the JavaScript and all that kind of stuff. And as you click on a button, it'll fire off another one with the response. Maybe you modify the DOM some more.
So for something like Google where there might be thousands of search results,
Mhm.
is it, I mean, I guess just optimistically rendering the page you're on and then making other requests, or are those, is it requested all of that information in your search?
So when I say Flatiron School, and it tells me, it gave me back 18.9 million results. It didn't give me 18.9 million results back in my response. It just told me that there are this many. So once it hits this server, who knows what's happening there? We can make some guesses, but one of the things it's probably doing is, okay, there's about this many results. Here's the first 10. That's what we're getting back. That's what we're showing on the page. And for that React challenge that I sent to the Hashketeers earlier in the week, I actually had a really fun time making what, if I were designing the Google search results page, what I think that API response should look like. So this was component hierarchies. This is how I would structure that response. I got my search results. Some of them have deep links to them. Some of them have platform links. Some have cards they link to. I also want a count of the results. I want to know how long it took. Those like kind of Q&A panels that come up. It maybe looked up any questions it wanted to ask, or the questions and answers, and links to more. There's these knowledge panels on the side. And so I would probably want something like this. Adam Enbar has his own search results. Womp womp, Avi doesn't. These little pictures here they're not actually like image URLs really. They're called data URLs. It doesn't give you a place to send an HTTP request to get that image. It actually has all of the image data in the URL, which is kind of cool. Profile links. Number of additional results, but it doesn't actually send those back to you. And so when I click on the next thing or something, that's a completely separate request. Great question. What else? Other questions about how any of that works? Yeah, Carl.
How automated is, like, sends a first request, puts the HTML back,
Mhm.
goes through it, says, oh, I need styles.
Mm-hmm.
How is it generating that styles request on its own?
From your link tag. It goes, I know how link tags work. I look at the href and I make an HTTP GET request to whatever URL that is.
Okay.
And it also does DNS lookup with that and all the other kind of stuff.
Think it even like lower than that, like how, like that's very automatic. Like
Yes,
you have to go through-
extremely.
Okay.
Oh, one other thing. This is the next level down. Nobody needs to understand this to get a junior job. I fucking hope. Port 443, huh? The HTTPS protocol? Before any of that happens, there's a thing called a TLS handshake. Goes, okay, cool, this is the IP address, HTTPS, no problem. Before I fire off this request, I do what's called a TLS handshake so that we can send encrypted messages to each other. And that is absurdly complicated, and it happens in like just a heartbeat. It's so fucking fast. I have no idea how it works this quickly. But if you go to my knowledge wiki, I have these are the steps, basically. And all of that happens in like milliseconds. Client server independently create 384-bit master secret by hashing the pre-master secret and the 2 random numbers that were generated earlier. At this point, the random numbers and pre-master secret are discarded. And then every time you send something to HTTPS, you send a 384-bit master secret and split into 3 128-bit sections. Super complicated, but this is what makes it so that if I have access to the router for the building, I can't see your traffic. Because remember, we send over the body of these requests. That would include something like your username and your password. If I can get somewhere else in the network before it gets there, I can see your password. Every time you type in login kind of thing. If you're not using encrypted traffic, like I can snoop on stuff in the network if I want to. Not if it's encrypted. Encrypted means only me and Google know what the contents of this message are. And we make that agreement on how we're going to encrypt and decrypt things in like literal milliseconds. Amazing. Yeah.
Question on speed, and this is coming from just kind of a consumer lens.
Mm-hmm.
But I feel like, over the last 15 years, obviously the internet has gotten a lot faster.
Yep.
Does it seem like people still care about that, or are they caring more about functionality? Because now you're getting to a point where I go to load a Google site, I guess I don't really care how fast it is. Does that
Sure.
question make sense?
That's a super good question. But complicated answer. So, yes, performance still matters. Still matters a ton in a couple ways. One is that Google has done study over study over study about how much latency affects bounce rates. So this is, you try to go somewhere and it's slow to load and you go, fuck this, I don't actually care that much. And you just leave, it's bouncing. So they found, and this has held true year after year after year, that a latency over about a second, extremely steep cliff. Something takes more than a second to load, people go, maybe it's broken or something, I don't know. A second. And so what's hard for us as web developers is the way that we get these cool, awesome, modern apps is by shipping the entire app down to the browser instead of just running it on the server. So Rails, like the way that we didn't teach you to make Rails apps is your whole app lives on the server. I ask for this thing to get added to the database, and it does it and just sends me an HTML page instead of giving me the data. So modern app works, hey, I want develop Denver, cool. Here is a relatively empty HTML page and a 3 megabyte JavaScript thing that is the entire app. And you run it all locally, and so it feels fast because we don't have to make these network requests quite as often. Problem is those huge ass JavaScript files are fucking slow. We still have to transmit them over HTTP. And so we're in this constant tug of war between like, all right, well, how much functionality can I put into that? Can I break it up? This is like pretty bleeding edge in the front-end framework world right now. What if my app is split into 5 different big-ass JavaScript files, and when you hit that part of the site, we just give you the next big chunk? But all of that is to try to keep that bounce rate as low as possible. And the other part of the answer is that none of this stuff is that bad on this. or this phone that was once $600, stuff's not that bad. If you're on a metered internet connection in Africa on like a fucking Boost mobile phone or something, not quite as good. And kind of depends on the app, but a lot of that stuff you go like, oh, well, I mean, they're not buying anyway, except they are. And they're just because the infrastructure in their neck of the woods is like not particularly good internet or is metered. So that's like you pay per megabyte. And so they really don't like it when you send giant ass gerbil script files. A lot of times they do still need to buy things over the internet. And so speed matters for that, because if your app is slow and somebody else's isn't, they're going to use somebody else's. So yes, performance still very much matters. And like there's I think tech people in particular catch a lot of shit, deservedly so, for only tailoring their apps for things that work on MacBook Pros and $600 phones. Instead of like I saw like yesterday the penetration rates on like adoption of 2G, 3G, 4G was like something like 60-70% of the United States is still on 2G. So take that for what it is. Cool. Other questions about this? So to review, you type google.com in your browser and hit enter. Looks up the IP address for google.com on your computer, router, your ISP, wherever your ISP tells it to go, root DNS server, finds it, propagates it down. Oh, I think I didn't show you on that. And this A record, every 300 seconds. That's how often this expires. It's been more than 300 seconds since you asked for this. Ask again. I should probably kick that up. It slows down the site to do it that quickly. But when you're doing a lot of like changes and moving stuff around, you also don't want to have to wait one day to see whether or not your change happened. All right. So we resolve the URL to an IP address. We make an HTTP request to that IP address at whatever port matches the protocol we're using. Goes to the server. Server responds. HTTP response, generally including an HTML body, especially if we're going to google.com. It starts parsing through that HTML, adds in any other things that it's asking for, images, JavaScript, style sheets, any of that kind of stuff. And your browser ingests that, turns it into the DOM. The DOM is rendered by your browser. Ta-da! That is this internet of ours. So I want everybody to give the question another shot. Any questions before you do? Three minutes. pencil down. So if you'd be so kind as to Slack me the thing that you wrote, if you wrote it by hand, just snap a picture, send it over. Any last questions before we wrap? Going once, twice. Enjoy your lunch.